Welcome back to Syntax Grid. Today, we're diving deep into one of the most powerful techniques in machine learning, L1 regularization, or what's popularly known as lasso regression. Introduction. Lasso regression is a method that not only aims to fit a predictive model to your data, but also does so in a way that helps select the most important features. By applying a penalty to the absolute values of the coefficients, it forces some of the less important ones to shrink to zero. In essence, it performs both feature selection and regularization, making your model simpler and potentially more robust. Key goals for the video: understand what L1 regularization is and how it works. Explore its mathematical foundations and real-world applications. Learn through a practical example, demonstrating its ability to simplify and improve regression models. Compare L1 with other regularization techniques to highlight its unique strengths. Let's get started and see how lasso regression can add value to your data science toolkit. What is regularization? Regularization is a technique used in machine learning to prevent models from overfitting the training data. Overfitting occurs when a model performs exceptionally well on training data, but poorly on unseen data due to capturing noise and complex patterns that don't generalize well. Regularization introduces a penalty term to the model's loss function, which discourages it from making overly complex predictions. The mathematical representation is formula for L1 regularization, lasso regression. The formula for the cost function in L1 regularization is given by, let's break this down term by term. Residual sum of squares, RSS. This term measures the error in your model's predictions. It is defined as the sum of the squared differences between the actual values, y, and the predicted values, I hat, I, from your model. The goal of a regression model is to minimize this error term, ensuring accurate predictions. Lambda, regularization parameter. Lambda controls the degree of regularization applied to the model. A higher value of lambda means more regularization, leading to greater penalties for large coefficients. Choosing the right lambda is crucial. It balances the trade-off between fitting the data well, lower RSS, and keeping the model simple by shrinking coefficients. Sum of the absolute values of the coefficients. This term represents the penalty applied to the model's coefficients WEW. L1 regularization uses the absolute value of the coefficients, which means it can drive some of them to exactly zero if their contributions are not significant. This results in feature selection, making L1 particularly useful for high-dimensional data where only a few features may be relevant. How L1 differs from L2 regularization. L1 regularization, lasso, applies a penalty proportional to the absolute value of the coefficients. This leads to sparsity. Many coefficients may become exactly zero, effectively excluding some features from the model. This makes L1 a good choice for feature selection and creating simpler interpretable models. L2 regularization, RIG, applies a penalty proportional to the square of the coefficients. Unlike lone, this doesn't lead to sparsity. Instead, it tends to shrink all coefficients gradually, but keeps them non-zero. Coding demonstration. In this section, we'll demonstrate how L1 regularization, lasso regression, works using a text classification example. 1. We first import necessary libraries, including NumPy and Pandas for data manipulation, scikit-learn modules for machine learning tasks, and count vectorizer for text feature extraction. 2. We create a simple dataset for demonstration. The text column contains short phrases, while the label column indicates whether the text is spam, 1, or not spam, 0. 3. We use the count vectorizer to transform the text data into a sparse matrix of word counts, bag of words representation. The variable x contains the transformed feature matrix, and y holds the labels. 4. We split the data into training and testing sets, using train-test split to evaluate the model later. Applying lasso regression, logistic regression with L1 penalty. We create a logistic regression model with an L1 penalty, using the penalty equals L1 argument. The C parameter is the inverse of the regularization strength lambda. Smaller values of C increase the penalty, shrinking more coefficients to 0. Here, we set C equals 1.0. We display the feature coefficients learned by the model. Features with coefficients close to 0 or exactly 0 have minimal or no impact on prediction, demonstrating how L1 regularization eliminates irrelevant features, sparsity. Hyperparameter tuning for lambda using cross-validation. We perform hyperparameter tuning using a grid search over different values of C, which indirectly controls lambda. The grid search feed method performs cross-validation to find the best value of C that minimizes the model error. The optimal value of C is displayed and the best model's coefficients are printed. This shows which features remain significant under optimal regularization. In this video, we delved into L1 regularization, Lasso regression, explaining its role in simplifying models by reducing large coefficients to 0, making it a powerful tool for feature selection and preventing overfitting. We began with a brief overview of regularization, emphasizing how L1 works by creating sparse models. Next, we provided a mathematical explanation, breaking down the cost function, which balances the residual sum of squares, RSS, and a regularization term controlled by lambda. We highlighted how L1 differs from L2 regularization, focusing on its ability to eliminate unimportant features. Following this, we showcased a visual example using text classification, demonstrating how lasso regression shrinks some coefficients to 0 and effectively selects the most important features, while briefly touching on hyperparameter tuning for \lambda using cross-validation.
Thanks a ton for watching. If you're excited to keep leveling up in machine learning, we've got you covered. Hop over to explore our fun and insightful videos on regression techniques and classification methods in supervised learning all right here on Syntax Grid. We dive deep, have some laughs, and make it easy to learn. Can't wait to see you in the next one. Stay curious and keep exploring.